Hello everyone. So today we'll be talking about self-organizing maps. Self-organizing maps is again a generalization of k-means clustering. So what we are trying to do is we are trying to get clusters via two-dimensional representation of the data. Okay. So we construct some grids in two-dimensional space. Those grids can either be hexagonal like honeybee type of structure, or that can be rectangular, and then via those grids we try to represent objects. Means, so if I have hexagonal grids like this, so these are my grids, then all our objects would actually be assigned to one of these hexagons. Okay, so you try to divide objects into such hexagons. Okay, same thing can happen with usual rectangular type of structure. Okay, so you divide objects into these. So what is the procedure? So let me first write down the procedure. As I said in the earlier lecture, multidimensional scaling is actually used in SOM, self-organizing maps, because you need this 2D representation. So MDS actually tells you how you can represent higher dimensional data, higher dimensional cluster of points or a group of points in lower dimensional plane. So that thing is used here. Okay. So first you construct such grids, and then like clustering you have to proceed. So construct such hexagonal grids. So grids actually would be automatically constructed by your seed points. Construct hexagonal or rectangular type of grids. See, you can't have circular grids because otherwise there would be gaps in between. Okay, if you need continuity, you need to have such types of grids. Triangle is I think possible. So this is also okay. But then you can't, okay. So construct hexagonal or rectangular grids. We don't, as I said, we don't have to actually construct grids. They get automatically constructed if you choose, some cluster center type of thing. Then locate the grid point, which is also known as cluster center. Locate the grid point or cluster center closest to every object or observation. So closest to observation O. Okay, closest to observation O, a particular observation. Let that grid point or cluster center be MJ. So we are in jth cluster, it means be denoted by MJ. So originally this MJ is in p dimensional, right? So it's actually a p dimensional point. You are, by locating here, we are trying to get its two-dimensional representation. Okay. Now update the means of neighboring clusters. Update the means of neighboring clusters as well as jth cluster. Update the means of neighboring clusters as well as jth cluster. How do you update? Because you have added a new observation, you have to update it. So you update as mi is updated as original mi plus alpha times o minus mi. Okay, mi is updated as mi plus alpha times o minus mi. So because you are adding this observation O, you have some contribution from that observation in the new cluster mean. And as I said, all these are p-dimensional. Alpha is of course a constant. When I say it's constant, what I mean is alpha is a real number, but it need not stay constant throughout the entire clustering process, throughout the entire algorithm. It can vary. Okay, so alpha is kind of learning rate. So initially it can be high, whereas later it can be low, so that the clusters stabilize gradually. Okay, so alpha, as I said, is kind of learning rate, because you are changing the seed due to introduction of new observation, and alpha plays a role in it. So alpha is learning rate. Now how can you choose alpha then if you don't want it to be constant? So alpha may change in the process. So initially you may have higher alpha. So generally you initially take fast learning rate because things are, you want to first get some decent clusters. So initially higher learning rate. So maybe you can let it go from 1 to 0.04 over first 1000 steps. Okay, and then from that point onwards you may again let it go from 0.04 to 0 in say next 1000 steps. Okay, so something like that can happen. So initially you have high learning rate, it goes on decreasing, and later it decreases very slowly, but obviously it is low. So you go on updating the clusters and you keep repeating this process. Okay, so this step 2 and 3 we have to keep repeating till we get stable clusters. Okay, so repeat 2, 3 till convergence, till we get stable clusters. So it is, as I said, as you can see here, it's generalization of k-means. In k-means also we update the means when we introduce a new observation. The only difference is here, instead of updating mean of just that class, we are updating neighboring means also. Okay, so somewhere I should write here this ith cluster. So ith cluster is neighbor of jth cluster. Again, definition of neighbor, so either they share a boundary or they share at least one point. We have to define. Ith cluster is neighbor of jth cluster, or sometimes they may not share even a boundary or a point, but they may be within certain distance. Okay, so everyone in the vicinity is affected by introduction of new object, hence all their means are updated instead of updating just mean of that group. In that sense, this is generalization of k-means. Okay, we said here alpha can decrease linearly, etc. But so sometimes alpha can be taken as function of distance of the neighbor also. Means the neighbors which are close, for them alpha may be high. Neighbors which are far away, for them alpha may be low, because they are going to get less affected by new addition of this observation. Okay, so in that case alpha has to be function of that distance. So you may write mi as mi plus hij t. T is of course time, so and o minus mi. So Hij is dependent on distance between ith and jth cluster. So alpha t is learning rate at that time point, means at that step wherever you are in the iteration, e raised to minus dij upon say sigma t square. You can take something like that. Okay, so as I said, it is minus dij. So if distance is high, then hij would be low, because that cluster should be less affected by introduction of new observation in jth cluster. Okay. Another option is this entire quantity. Instead of this, we can have something like eta t. Again, eta t is kind of learning rate. Eij O minus mi, where Eij is something like Gaussian density with j as mean. Okay, so Eij can be 1 upon sigma t root 2 pi e raised to I minus of I minus j whole square upon sigma t. Okay, so it's like Gaussian density. Okay, so as I said, learning rate can be either the function of the iteration number or the step at which you are, and it can be specific to each cluster. So clusters which are nearby the cluster in which you are adding a new observation should be affected more than clusters which are far away. Okay, so these are two different examples of learning rates, but you can have some similar modifications further. So, and you go on repeating this process till you get convergence, that is, till all the observations are settled in one cluster, and this is nothing but self-organizing maps. Okay, so as you can see, it's another unsupervised learning algorithm which can be used for clustering. So we'll stop here. Thank you.